So once you actually do have a meaningful question, your next step is to gather your data, to actually get the data that would be necessary to give you a meaningful answer. And so there's many ways that this can be done. You could be given data. For instance, this week we'll give you guys some pathology image data, which you'll see after this lecture. You might need to download data. So if you've ever used Kaggle, there's a lot of data available that you can download and analyze yourself. You could also scrape data off the web. So if you're interested in trying to look at Twitter data, for instance, like I mentioned at the beginning, Python has an API where you can actually scrape tweets and analyze them yourself if you wanted to. Or you could have to collect the data yourself. This is super time consuming. So if you needed survey data, you might need to design the survey, send it out to people, and organize and process it all by yourself. Or it might be some combination of these. So in terms of effort, given the data will be quite easy. If you have to collect it yourself, will be much harder. So after we've actually gathered the data, really the most consuming aspect of data science is cleaning and exploring it. So you always want to understand your data before you put any sort of machine learning model on it, before you do any sorts of analysis. Make sure you know your data, you understand its peculiarities. And most data scientists that you ask, you could ask them at lunch this week if you wanted to, will say this is where they spend most of their time. So maybe not the most glamorous aspect of data science, but where we do spend a big chunk of time. So why do we do this? So this is just one simple example. So what you can see here is I have two variables, x and y, and let's say I know ahead of time that they're bounded between 0 and 0.5. But I have this one outlier here that's actually above 0.5. Well, the true model for these data is this dotted line here. Had I cleaned my data, thrown out the observation that was erroneous, I would have been able to estimate that truth. If I keep the outlier in the data, you can see I get an entirely different line that's fit to the data. So you can tell that if I don't clean my data appropriately, this is a super simple example, but you can impact the conclusions, right? You make an error here, everything downstream is going to have an issue. We've got a question from Matthew. Are outliers? Oh, outliers are very, very common. So typically, you don't want to just throw out an outlier. You'll ask your collaborators why an outlier might occur. That's usually where you start. And sometimes you do need to keep them in your data. But I think every project I've worked with has had outliers. So often the first thing you do when you get a data set is you make lots and lots of plots. Most distributions of variables are going to have super, super long tails. And that's just because there's a lot of variability in everything we see. So great question, Matthew. So first piece, we want to clean our data because it can impact our conclusions. Secondly, exploring the data allows you to verify any sort of modeling assumptions that you might have. So when we fit complex models, we want to know, do they actually describe the data well? If they don't, they're probably going to have really poor generalization. They're not going to perform well on a new data point if the model's a terrible fit. So we go to a lot of trouble to really understand, what does the data look like? Is the model we're using appropriate? And so once we've done all this sort of data cleaning, data exploration, we get to the fun bit, which many of you are probably excited about for this week, which is actually modeling the data. And so there are many ways that one can model the data. So you've probably heard a lot about neural networks, which you'll get introduced this week, but there are many other tasks in data science that people work on. And so typically data scientists come in two flavors. The first is a statistician like myself, where we typically think about three tasks that we work on with data: description, prediction, or causal inference. And I'll describe those to you in a second. Whereas someone who's a computer scientist thinks about whether a modeling task is supervised or unsupervised. And you've probably heard these terms, or you will this week. And so clearly there's three terms in one group, two terms in another, but they don't necessarily map to each other. It's just sort of a different way to conceptualize data. Statisticians are very focused on sort of the data generating mechanism, a data first perspective, whereas computer scientists often are more of a model first, thinking about what type of model might be appropriate for their data, which is sort of giving rise to this distinction.